again, last time sort of indicated I would talk about some of the more geometric examples. Last time, if you like, what I talked about is analogous to saying you can understand the isometry of the tree by thinking of it as homeomorphisms of the tree. Branch points are canonical enough that you don't really need to use the metric structure. But we have, in a lot of the interesting examples, spaces which are topologically identical, and it's only the metric that's different. And we need to use somewhat different techniques here. So, in particular, I want to talk about lattices and Lie groups. I really mean co-compact discrete subgroups. Finite volume lattices are similar, but they have their own complications. I'm going to stick to this simpler example. And examples, I think I wrote down last time all these three manifold geometries, these Lie groups that people are concerned about. So we have SL2C, which is H3, and SL2R times R, which gives us H2 times R. Anybody, I left off the two-sphere because, of course, the two-sphere is simply connected. So from the coarse geometry point of view, it might as well be the trivial group. Although I will point out there that every finite group is quasi-isometric to the trivial group, and not all of them act as a properly discontinuous co-compact group by isometry to the three-sphere in any useful way. So, ignoring finite groups does make a difference. Right, so these are basically the dimension 3 examples. There are also, of course, higher dimensional examples, famous locally symmetric spaces, say SLNR, lot SON, or if you want to think about it as the group, just SLNR modulo some discrete compact subgroup. So, just going back to the first thing we did, if you act properly continuously and co-compactly by isometry on something, then you are quasi-isometric to it. So if you've got a discrete co-compact subgroup of a Lie group, it is quasi-isometric to that Lie group, whatever left invariant metric you want to put on there. Or, because it's sometimes more convenient, the Lie group modulo a compact subgroup. Just change QI type to mod up by something compact. So these geometries break up into a couple of different cases. Maybe I'll mention some things that we've seen. Right, this one, and this one, and this one are all non-positive curvature. Cat 0, we've seen get talked about quite a lot so far. These other three are not. They're somehow different, although the reason 4R3 is off here at the end by itself. Although it is non-positively curved, it doesn't really fit the sort of techniques we need for these others. So to start with these, because they have some of the nicer geometry, I'll just remind you, we've seen a bunch of times now this cat 0 condition. spend a lot of time on this. You've seen it a lot in Unity. You probably knows what we're talking about, but if you draw a triangle in your space, which makes sense when we're talking about spaces which have geodesics, this triangle has some side lengths. Only real constraints that they better satisfy the triangle equality. And then, of course, there's a Euclidean triangle with the same side lengths. And now you can ask how this whole triangle, not just the three vertices, behaves as a metric space compared to the corresponding Euclidean one. So, for example, you can ask how far is the midpoint of one side from the opposite vertex. Ask, is that closer or farther than it would be in Euclidean space? And statements saying that it's not any farther, essentially what cat 0 tells you. Okay, and this is some nice generalization of non-positive curvature from the Riemannian setting to these arbitrary geodesic metric space settings. You still have Cartan-Hadamard type results. Gives you the sort of topological information you might have. Unfortunately, well, I want to have that up there. Cat 0 is not QI invariant. Cat 0 really doesn't play very well with QIs, and the reason is sort of implicit in this picture. This is all about the behavior of geodesics. Okay, now you take your geodesic triangle and apply some quasi-isometry. The image of your geodesic is probably not a geodesic. It may not even be anything like a geodesic. Okay, and then, so what that tells you about the domains, passing from the domain to the range is rather confusing. So you don't have a good way to relate geodesic triangles on one side, those on the other. And this theme of not having control of quasi-geodesics, or images of geodesics under quasi-isometries, is sort of a constant theme in where things go wrong. So let me just give two examples. One was already mentioned. There's a QI just from R2 to R2. It's going to send the origin to the origin, and in fact send every ball of radius r, the circle of radius r, to the circle of radius r, except by rotating some amount that varies with r. Rotate by some function of r. And now it's fairly easy to compute what's required here for this to be a quasi-isometry. If you imagine here you are in the ball of circle of radius r, and you go out 1 unit, then you're going to rotate over here by some amount, say f of r, and then your other point is going to be 1 farther unit out, and the rotation is going to be f of r plus 1. Really should have used more than one color there. But these 2 points that were on the ball of radius r and r plus 1, just directly along a radial line, so distance 1, get rotated by slightly differing amounts. How far apart they end up being depends on the difference in angles and the radius. It's roughly the difference in angles times the radius. So you need, if you like, the rate of change of your function to be no bigger roughly than 1 over r. So something logarithmic is the standard example. We take something like f of r is log of 1 plus r. We get something that works just fine. It's a quasi-isometry from R2 to R2. But if you take some ray, I already saw this picture I think in one of the other slides, it starts rotating around and it ends up in some logarithmic spiral. So not only is it not a straight line, if you like, it ends up limiting, spiraling around the entire boundary at infinity infinitely many times. So the images of geodesics can be pretty bad. That's roughly the point here. And what you learn about triangle built out of things like this is not so. This makes sense. So that doesn't really prove that being cat 0 is a QI invariant. Of course, R2 is cat 0, whichever side of the tree you want to have it on. And it just proves that geodesics aren't well behaved. But in fact, to eliminate some of our geometries up there from the beginning, SL2R tilde and SL2R cross R are quasi-isometric. Just to remind you, this one you generally think of as being a hyperbolic plane cross R. SL2R tilde is one of these weirder Lie groups, right? It's just the universal cover of SL2R. SL2R is a three-dimensional Lie group. It's not simply connected. The circle you get by rotations is actually homotomically non-trivial. So it has a universal cover, which is also a three-dimensional Lie group. It no longer has a compact circle on outline, we just unrolled it. So it is just, this is itself just some three-dimensional geometry, and have a discrete co-compact subgroup of here. And I think the usual way to think about this geometrically is to think of your hyperbolic surface. Of course, also what you would have in this case. Now, in this case, you just add an extra R direction. You're just taking the product, or if you're thinking in the compact setting, you take the product with the circle here. So you want to take a non-trivial circle bundle over this surface. And it's not a mysterious one, it's just a unit tangent bundle. Okay, so if you think about the geometry of unit length vectors on a hyperbolic surface, that gives you a compact three-manifold model on SL2R tilde. Yes, I would point out that it is, as always happens with universal covers of groups, this is just an extension of SL2R by pi1 of SL2R, okay, which happens to be Z. It's a central extension, it always has to be. It's just not a trivial central extension, so it's not the same as the product. But it turns out the fact that triangles are thin is closely related to why this is true, that it is quasi-isometric to the product even though it's not the product. And this is actually another common source of trouble. Somehow things with center and things that behave like center are really problematic from the QI point of view. Just the simplest explanation for that is that when you translate by an element of the center, you get an isometry of your group, but it's also a bounded distance from the identity. Just it's like a translation on the real line. It just moves every point some fixed amount. So from the point of view of calling QI's equivalent, it's not there at all. It's equivalent to the identity. So when you talk about these QI's modulo this bounded distance equivalence, you sort of need to make things actually work out well. You're throwing away the information about the center. So there are lots of bad examples coming from central extensions that somehow aren't detectable by QIs. This is one of the simpler ones. I guess I'll mention maybe nil. Instead of working with the surface hyogenous, you work with the torus and look at its unit tangent bundle. Anyway, nil and R3 are not QI, and it has to do with the fact that the Euclidean plane does not have thin triangles, while the hyperbolic one does. So, all right, so the upshot of all of this is that while being cat 0 is nice from a geometric point of view, doesn't necessarily help us that much from a quasi-isometric point of view because we don't have control over what geodesics are doing. So in negative curvature, quasi-geodesics do stay close to geodesics. And this could have been the theme of all three lectures. And this is the fact that your quasi-geodesics actually track geodesics all the time can be taken as a definition of delta-hyperbolicity. It's equivalent to delta-hyperbolicity. And it makes a lot of things about the large-scale geometry of delta-hyperbolic groups better behaved. It basically means you don't see cancellation unless you see it locally. So for a path in a tree, it's either an embedded geodesic or you see immediate local backtracking. Detect this locally. And this passes to negative curvature. And this is what this is behind the co-compactness that Chris was talking about. It's behind why hyperbolic groups have all sorts of quotients all over the place, which plays a key role in this angle-wise machinery for virtual fiber and virtual hockey. It's been used to build lots of exotic examples of groups, like taking weird quotients of hyperbolic groups, Burnside groups, and groups with only two conjugacy classes, finally generating groups that can't act on anything contractible without a global fixed point. So this could be a whole theme. I'm not going to do that. I'll just mention on our list here the only hyperbolic thing on that list is hyperbolic 3 space. Coincidence of names is not really coincidental. And all I will say about QI stuff here is that in the hyperbolic setting, because geodesics are reasonably well behaved under quasi-isometry, this boundary you get by following rays off from a point is invariant under quasi-isometries. And you can translate more or less anything you want to know about the sort of quasi-isometric geometry of hyperbolic things into quasi-conformal geometry. The boundary of infinity, which in this case is the two-sphere. And there's, of course, a long history of quasi-conformal analysis on the two-sphere and results of Tukia more or less directly translate into saying that anything quasi-isometric H3 is itself a lattice in H3. The answer is the question there, but it has a very different analytic flavor, and I won't really say anything more. All right, so not everything's hyperbolic. But I gave you a weird example of a quasi-isometry of R2 that spins things around and moves away from the origin. It's rather harder to do that systematically for a self-quasi-isometry of the hyperbolic plane crossover. Because remember, this R direction is different from a ray in the hyperbolic plane, even though there's a copy of R2 sitting in there as a product of the geodesic in H2. With the R direction, rotating those around and compatibly dragging the rest of the space around is not so easy. And in fact, for quote complicated non-positive curvature spaces, the idea is to control maximal flats. Okay, so it's the maximal dimensional geodesically embedded Euclidean space. In the hyperbolic case, there are no copies of R2 inside something hyperbolic, so it's always just a copy of R1, which is the same thing as a geodesic. Not an isometric thing, R1. When we have more Euclidean directions, want to see what we can do with them. So for example, in H2 cross R, these are the same thing. Geodesic in H2 cross R, that's all the isometric copies of R2 that there are in there. Now, if we knew what happened to these under quasi-isometries, we'd be in pretty good shape, because in particular, these R directions are special. There are lots and lots of copies of R2 in here that intersect. When they intersect, it's always in the cross R direction. Everything just has this one Euclidean direction to take product with, and the geodesics in H2 can cross in all sorts of ways. And this gives us some rigidity of what's happening within each R2. Now, this sort of vertical direction in R2 has to be preserved because it's intrinsically determined by the rest of the space. And that at least should tell you, there's a hint, you can't just rotate around like crazy inside of this flat with the self-quasi-isometry of H2 cross R. And in fact, all you really can do is sort of shear in these directions. You have to more or less leave the vertical direction alone, and you can shear by different amounts in different directions. And in fact, for instance, if you take, I'll just point this out as a good example for thinking about how bad or good things can get. You can take f from H2 to R, any Lipschitz function. And there are, of course, a lot of these. And then you can define a map from H2 cross R to H2 cross R, which just sends x t sheared by this function that's allowed to vary in any Lipschitz way you want. These are all self-quasi-isometries. They're all by Lipschitz homeos of H2 cross R.
Why can't you rotate in the hyperbolic plane direction?
Oh yeah, you can. This is just if you're doing the identity in the hyperbolic plane. You can, of course, also do any isometry of the hyperbolic plane you want across doing nothing. And in fact, right, so those are so what I wanted to say is if you know that these planes are roughly preserved by quasi-isometries, then you know that this sort of vertical foliation H2 cross R product structure is preserved. And that tells you that any self-quasi-isometry of H2 cross R is going to be doing something on the H2 factor, in the space along the lines, and then possibly some shearing along the lines. So there's, and this is in fact true on the nose. There's some map from self-quasi-isometries of H2 cross R for exactly this reason, down to the quasi-isometries of H2. Of course, you can take any quasi-isometry of H2 and take the product of the identity map back here. And then the kernel, the quasi-isometries, or the identity map on H2, are essentially these kind of shears. Okay, so there's some sort of, if you knew about structure theory of flats, you get some statement like this. And then what do? Well, I completely ignored all the hard analysis that tells you things that quasi-act on H2 can be turned into things that act on H2. This is Tukia and so forth. So a mystery group that is quasi-isometric to here will, by taking just of these space of vertical lines, be acting by quasi-isometries on the hyperbolic plane. That can be appropriately conjugated by some other quasi-isometry of the hyperbolic plane to turn into a group of isometries, the hyperbolic planes of some surface group. And then you get some kernel in the shears, which has to be quasi-isometric to Z to make the whole group be the right QI type. And then you get stuck because you've got a surface group and an extension by Z. And it's hard to know what to do with all these shears. And there's a good reason for that, because there are different central extensions which are in fact quasi-isometric. So you can't unravel it any further than that. This is the more detailed explanation of why somehow you can't unravel these central extensions. But everything quasi-isometric to H2 cross R is a central extension of a surface group by Z, at least up to an index. Just not necessarily the trivial extension. Now, I cited complicated over here. This barely counts as complicated. The fact that there are these directions which are the intersection of all these flats, and you can't find flats sort of running transverse to them, is a sign that it's not complicated enough. I will leave dimension 3 here for a moment. So this statement here, essentially, that I mentioned about things Qi to H2 cross R are central extensions of a surface group. Just do the equal. Now, for things that aren't products and really have lots of flats running around in all sorts of crazy directions, which you don't get in dimension 3, but you do get for other symmetric spaces. Irreducible, so not products, that's key. We don't have this H2 cross R sort of situation. At rank at least 2, so we're not looking at something hyperbolic. There really are higher dimensional Euclidean spaces floating around. If you want to, you can just think SL3R mod SO3. There's a ton of these things. In fact, the quasi-isometry group is the isometry group. And every quasi-isometry is on the nose already at bounded distance from an isometry. There's no flexibility whatsoever. This is slide or leave. Or the approach I'm suggesting to it here is really do the estimated form. And really shouldn't mention this without also mentioning theorems of Mostow and Margulis. It says, in this setting, I'm not going to list all the hypotheses, but every embedding of lattices among these spaces so in particular, every isomorphism from one lattice to another, just on the group theory level, comes from an isometric embedding. Symmetric spaces. And in fact, if you're in the case where it's not an embedding, but actually an isomorphism between lattices, you can allow rank 1. As long as you don't try to talk about a hyperbolic plane. Mostow rigidity certainly works for hyperbolic 3 space as well. And this, I bring this up mainly because it was the primary motivation for studying this question. Mostow rigidity and Margulis' super-rigidity theorems have been fundamental in a lot of studying lattices and Lie groups. And this is the natural sort of coarse analog, which at least for the Mostow case is strictly a special case of this. Maybe I'll say something about the embedding case a little bit later. But this was one of the first big goals of the subject, and it turns out to work out exactly the way you would hope it would. And the idea of the proof here is actually the same, in some sense, as it is in the proof here. Once you know what's happening to flats, the patterns of flats in these symmetric spaces form a building, a spherical building of higher rank, which is something I won't say anything more about. But Tietz has an old theorem that tells you all the combinatorial automorphisms, something like that, are in fact isometries. So the combinatorics of how the flats intersect each other and which flats intersect with each other flats is rigid enough to in fact force any quasi-isometry to be an isometry. Okay, the simplest case of that, I'll write it down explicitly. That works. All right, so yes, I should mention that I sort of implied here that the quasi-isometric image of a flat is a flat. That's not actually quite right. It turns out there's a finite amount of bending you can do. But the quasi-isometric image of an Rn is close enough to a flat that if you're going to do it to the whole space, the images of flats are flats. There are a lot of technicalities I'm squeezing under the rug here. Want to see an example of a bad quasi-flat over lunch. Draw one. But, right, so as far as the rigidity coming from flats, there's sort of an easy illustration of this, which is that a QI of R2 saw in the H2 cross R case, when flats intersect like this, you may preserve this family of lines. You can permute them around, but you basically have to send those lines to lines. That's not too rigid. You can preserve a second set of lines. You start to get more rigidity, but you can still be a product of any two quasi-isometries of R with R in 1. You add a third affine foliation like this, and a quasi-isometry that preserves all of these is affine. Is in the sense of is about a distance from an affine. So, in fact, once you have three different independent directions where flats can cross each other, you can't do anything on a flat except an affine map. And that somehow propagates out to the whole space until the only thing you can do is an isometry. I guess I will mention, without trying to write it down, in the embedding setting, when you talk about a QI embedding of one symmetric space in another, there the situation is currently very unclear. You can construct all sorts of exotic QI embeddings. They're definitely not rigid in the sense that Margulis super-rigidity would pick for you, even for the nicest of higher rank symmetric spaces. Although there are some pairs where rigidity works just fine. So I'll just say this is ongoing work, aligned with David Fisher, trying to figure out what's going on with QI embedding. Maybe I'll mention some of the current issues in the problem session. It's still quite mysterious. So, I just sort of discussed this one. And I told you it's the same as this one, so we're okay with that. I told you I'm going to ignore this one, so we're okay with that. That leaves us with these three. And here without stating another famous theorem. You remember at the very beginning I talked about distinguishing the hyperbolic plane from R2s by looking at the growth rates of balls. Well, turns out that having balls grow just as some polynomial of the radius is really quite restricted. It's not that surprising. You start multiplying your generators together at random, you get exponentially many words. Having these collapse down to only polynomially many different group elements requires a lot of relations. And so there's a theorem here of Gromov. Having balls polynomially bounded size is actually completely equivalent to having a finite index subgroup which is nilpotent. Right, so, and it's not hard from there to handle nil and R3 specifically because there just aren't very many three-dimensional nilpotent groups, and you can cook up ad hoc invariants to tell those two apart. But I will point out here that we get no control at all over individual quasi-isometries. This is very different from the sort of strategy we were pursuing in these other cases where we say every quasi-isometry is a fairly rigid structure, and that tells us that everything quasi-isometric to our group, in fact, basically acts on the same space. Here, it's just that this condition on the space is so strong, we can identify all the spaces that could possibly have it, right? But we don't actually have any idea what their large-scale symmetries look like. If you want another area that's more or less completely open, understanding what self-quasi-isometries of Euclidean space or nilpotent groups look like is something we just don't understand at all. And in particular, probably the most famous open problem in the field right now is that although we know being virtually nilpotent is a quasi-isometry invariant, we don't have much in the way of technology for deciding whether two specific nilpotent groups are quasi-isometric or not. You start listing invariants and telling them apart, but we have nothing like continuance. Right, so that leaves poor Sol sitting all there by itself, which is more or less historically accurate. So somehow Sol got famous, even though, I don't know. But, so it is also true, this is a theorem in line with Peskin Fisher, nothing exotic happens here either. Anything quasi-isometric to Sol basically is a lattice Sol. And in fact, it manages to be true here that the QI group of Sol is somewhat understandable. The difference essentially between Sol and nil is that Sol is just a semi-direct product of R with R2 via some diagonalizable matrix. And the fact that there's exponential stretching as you move off in this semi-direct product gives you some hyperbolicity hiding inside of here, even though the group's not hyperbolic. And that allows there to be some rigidity, whereas in this group certainly has exponential growth. Unlike sort of here where there's nothing. But the idea, and this works to a certain extent here as well, like coarse analysis. So we're saying what we want is to understand what a quasi-isometry can do to geodesics, quasi-geodesics. And I gave you a crazy example of R2 to show that the answer is you can do a lot of crazy things. But, all right, forget that we're doing large-scale geometry and go back to small-scale geometry. If I want to know whether rectifiable curves are well approximated by straight lines or not, more or less the same question, I'm really just asking a question about differentiability. Are the images of my curves locally well approximable by lines? And it says, does my map locally send lines basically to lines? It's just another way of asking whether something's differentiable, if you interpret it correctly. And there's a classical theorem of Rademacher's that tells you a map which is bi-Lipschitz is in fact differentiable almost everywhere. Okay, so the only thing I'll say about this last bit is that there's a sort of coarse Rademacher type technology which says that quasi-geodesics are mostly well approximable by geodesics. At most scales. Okay, so we end up with a few more constants than you have in Rademacher. You don't get to pass to a limit. You have to worry about all the different large scales somewhat independently. I won't try to say what this means, because that never works. But I will point out what happens to this geodesic ray in R2. We had this ray that turned into this logarithmic spiral. And the point here in this particular example is just that, okay, near the origin there's some weird winding. Let's ignore that. That's only a tiny part of the plane. We can throw that away. If we go pretty far out along this ray, then what we get is something over here. The sort of winding is slowing down. It has to be a logarithmic spiral for this to work. So as long as we're really quite far out compared to the length of the geodesic segment you're talking about over there, the difference in radius is the difference in radius is pretty minimal. We're rotating very slowly, and this is in fact difference in angle. Difference in radius is in fact almost linear. In fact, this picture is sort of bad. Logarithmic spiral does in fact look like it runs almost straight away from the origin, because the angle is moving very slowly compared to the radius. And in fact, once you go far enough out, long segments here look quite close to straight lines over here. And there is some bending, but they're well approximated that way. You just have to ignore what's happening near the origin, where the curling is happening too quickly. And what we prove is some, unfortunately, painful generalization of that tells you that most geodesics, most of the time at most scales, are just going straight. One has to be careful about making all of that precise, and then making sure that having most geodesics work out is enough to capture whatever geometry you need. And in fact, that's the difference between these two cases. Because of the hyperbolicity in here, knowing what happens to most geodesics actually turns out to be enough to bootstrap onto the whole space, and everything is fairly well understood. Knowing what's happening in these cases doesn't really tell you a lot. Although most of the invariants we do have distinguishing different nilpotent groups from one another come from this sort of large-scale differentiation technology, although in that particular case it's earlier in advance. stop 10 minutes early, or I can provide details on whatever piece here people are curious about. Yes. I guess I should say there are definitely higher dimensional nilpotent groups. As I said, the situation there is completely mysterious, more or less, modulo some large-scale derivative information. There are also higher dimensional solvable groups, which do have some exponential stretching. And yeah, that's ongoing work, and it's very unclear to what extent the technology here generalizes and which of the groups it can handle. So that's still actively in flux. So it's definitely, just as with R3 and nil, it's easy to pin them down because you can get that they're nilpotent, and then they're only dimension 3, and there's not a long list. It's important to hear for Sol as well that we're dealing specifically with this particular solvable group, the bootstrap up using these almost every geodesic statements. So there's, for these amenable groups or things with not any real negative curvature or non-positive curvature involved, it's still fairly wide open what quasi-isometries look like and what's quasi-isometric as well.
Were there some other problems that you were going to, you said you were going to mention them during the problem session?
Oh, well, so I was going to say,
If you wanted to emphasize them here, then we'll even get them on video. So people
Right.
will revisit them.
so maybe I'll say something about this QI embedding problem. So, we gave you this example of a bad quasi-isometry of H2 cross R that just sort of shears in the R direction. So it's not very close to being isometric. That had nothing to do with the base being H2. So in particular, we can take any x. X R Lifshitz. And then the graph gives us a QI embedding x and x cross R. So if we have an extra R direction to play with, it's fairly easy to do QI embeddings. And unfortunately, while we can't do weird things like this inside individual symmetric spaces, from one symmetric space to another, we often can, because there's often a lot of room. So for example, SLNR cross R sits as a totally geodesic subspace of SL n plus 1 R. So then you can stick SLNR into here in some crazy way and end up with some crazy QI embedding of SLNR inside of SLN plus 1R. So there's these same Euclidean space issues give us real problems for QI embeddings. Somehow they aren't a problem for super-rigidity. For Margulis' setting, once you have at least dimension 2 in the range, then the complicated pattern of flats is enough to make everything work. Somehow here it just isn't. Whenever you have extra Euclidean factors, things just get bad. So we focused mainly on the case if the rank, which is just the maximal dimension of the Euclidean space that you have in there, is equal to the rank of y and bigger than or equal to 2. Because you're dealing with two hyperbolic spaces. Say that there's some old work of Bonk and Schrum that tells you more or less anything hyperbolic at all embeds into hyperbolic n space for n large enough, quasi-isometrically. And the hyperbolic n space embeds into most other things you want. So there's very little understanding or control of what's going on in here. I guess I should point out, of course, even quasi-Fuchsian QI embeddings of H2 into H3 are rather complicated. So there's a lot going on in a hyperbolic case which just isn't under control. With range both have bigger Euclidean spaces in them and more complicated intersections. Turns out sometimes things are fine. So here's, for example, a theorem. Every QI embedding of SL and R into SL and C, where n there is at least 3, the rank is at least 2, is near an isometric embedding. On the other hand, this is one theorem, again related, there are weird QI embeddings SL3R into SP4R. So whether that means anything or not, I would point out, I put weird here in parentheses, but there are no actual embeddings. There are no isometric embeddings at all. So there's nothing to be near to. But there are QI embeddings nonetheless. Okay, these are both with David Fisher. And the construction here is really ad hoc. Okay, the machinery here doesn't work, and in this particular case, we can show that the reason for that. Exactly what embeds where and how is really quite confusing. And even in this case, the only things we can construct for weird embeddings of SL and R and SL plus 1R are in some obvious but not very precise sense perturbations of good embeddings. Right? This is really just the embedding of SL and R here isometrically pushed off of itself in some reasonable way. It's just a deformation, if you like, of the isometric embedding. That may be true. Something like that may be true for all QI embeddings. We just have no idea how to get a handle on them. In general, quasi-isometric embeddings are really not understood. Inverse maps are useful. Okay. All right, thank you.